Now we'll look at Kruskals' algorithm for computing the MST. This is an old algorithm that dates back over 50 years, but it's an effective way to solve the problem. The idea is very simple. We're going to take the edges and we're going to sort them by weight. And we're going to consider them in order of ascending weight. And the algorithm is simply add the next edge to the tree unless that edge would create a cycle. If the edge creates a cycle, ignore it and go on to the next one. Let's look at a demo of Kruskals' algorithm. Okay, so we have the edges sorted by weight, and we're going to take them in ascending order of weight. The smallest edge is in the MST, and so we add that to the tree. Doesn't create a cycle. Next smallest edge is 2, 3. That doesn't create a cycle. Next one is 1, 7. That's fine. Next one is 0, 2. Next one, 5, 7. Now, when we get to 1, 3, that one creates a cycle. And the algorithm says, creates a cycle, just ignore it. Next one is 1, 5. That one also creates a cycle, 1, 5, 7. Again, just ignore it. 2, 7 creates a cycle, not in the MST. 4, 5, that next smallest edge, does not create a cycle, so we add it to the MST. 1, 2 creates a cycle, 4, 7 creates a cycle, 0, 4 creates a cycle, and finally we get to 6, 2, which does not create a cycle, so we add that to the tree. At this point, we have an MST. We could check that we have v-1 edges and stop, or we can just keep going and see that the other edges in the graph create a cycle. And when we're done considering all the edges, then we have computed the minimum spanning tree. That's with Kruskals' algorithm. Consider the edges in ascending order of weight, add the next edge to T, unless doing so would create a cycle. Now let's look at what Kruskals' algorithm does on a very large graph. You get a good feeling for what it's doing. It's taking the small edges, and they coalesce together in little clusters, and eventually the edges get longer and longer, and they connect together the clusters. But initially, it's broken up into the very small edges. And after a while, if you look at the larger clusters, eventually an edge will come that'll connect them together. It's not going to be so easy to see how the algorithm ends. There's some long edge there. That's the longest edge in the MST that'll finally connect the graph. This simulation really gives a good feeling for Kruskals' algorithm. In fact, when we first had personal computers, I was fortunate enough to be at Xerox PARC, and I remember very well in the late 70s, this is one of the first algorithms that I wanted to see visualized on a personal computer. And I wrote a program at that time that produced pretty much this image. It's a very interesting way to look at MST algorithms. All right, so it's easy to implement. We have to prove that it computes the MST, of course, and we've done a lot of work setting that up, and we do so just by proving that it's a special case of the greedy MST algorithm. So what does that mean? Well, suppose that Kruskals' algorithm colors a given edge black. So say it's VW. So we'll define a cut that is the set of vertices that are connected to V. So it might be just V, but if there's any black edges connecting V to other vertices, we put all of those in the cut. So for that cut, there's no black crossing edge because it's a component. And the other thing is that there's no crossing edge with lower weight than VW. And why is that? Well, we haven't examined any of those edges yet, and they're all longer because we're considering the edges in increasing order of their weight. So this new edge that connects V somewhere else is a crossing edge of minimal weight, and so therefore the algorithm always finds a cut and colors the crossing edge of minimal weight for that cut black, and it's an instance of the greedy algorithm. Now, we still are a bit away from having an implementation of Kruskals' algorithm. So the question is, how do we know whether adding a new edge to the tree will cause a cycle? So you might think about how difficult that is. I've got a tree that's represented as a set of edges or however, and I have a new edge, and I want to know whether it creates a cycle or not. How difficult is that going to be? Well, it turns out way back in the first lecture of Algorithms Part 1, we had a way. Well, one thing we could do is just run DFS to check if we can get to W from V. That would take time proportional to V. But the union find data structure that we did in the first lecture absolutely does the job. It's just testing whether this edge connects anybody in the equivalence class corresponding to V with anybody in the equivalence class corresponding to Y, to W. And if it did, it creates a cycle. So union find is exactly what we need. So what we're gonna do is maintain a set for each of the connected components in the spanning tree that we've built up so far. And so if the new edge connects vertices that are in the same set, then that means it would create a cycle. Otherwise, we're going to be adding the edge to the tree, so then we just do the union operation and merge the set containing V with the set containing W. Those are the two things that we need to do, and those are the two things that union find does for us. So this leads to a very compact implementation of Kruskals' algorithm. Now, to consider the edges in order, we'll use a priority queue, a modern data structure. Let's take a look at every line in this implementation of Kruskals' algorithm. We're going to have a queue of edges. That's how we're going to represent the MST. It could be a stack or a bag, but we'll use a queue. And then the Kruskal MST algorithm takes a graph, and it's going to compute the MST in this MST. And to do that, it's going to use a priority queue, a min priority queue, minimum oriented priority queue of edges. We'll build that minimum priority queue. Now edges are comparable. We had a compare to method. So our generic priority queue code is going to work fine. And so what we'll do is we'll put all the edges in the graph into the priority queue. So that's building a priority queue containing all the edges in the graph. Alternatively, we could put the edges in an array and sort the array, but priority queue is a more elegant way to express this, and it is a way to look at more efficient algorithms as well. Okay, so that's priority queue, so that's a first data structure from part 1 that we're going to make use of. And then the second one is the union find data structure. So we're going to build a union find data structure for vertices because the spanning forest divides the vertices into equivalence classes. So then we go into the main loop, and the main loop stops in two conditions. We run out of edges is one, where we'd have a minimum spanning forest, or the other condition is we get to V minus 1 edges in the MST. As long as neither one of those is true, then we've got an edge in the priority queue, and we want to take the smallest one. We want to get its vertices, V and W, either and other. And then we want to check using the union find algorithm if they're connected. If they're connected, we don't want to do anything. If they're not connected, then we want to merge them and put that edge onto the MST. That's it. And then that's the full implementation. And then we have the edges method for the client to return the MST. It's quite a compact implementation of a classic algorithm using the basic data structures that we built up in algorithm part 1, data structures and algorithms of priority queue and union find gives a really fine implementation of this MST algorithm. So what about the running time of this algorithm? Well, it's not hard to see that it's going to compute the MST in time proportional to E log E. It's linear arithmetic in the number of edges, which means that we can use it for huge graphs. So this table is just a proof that summarizes the costs. We're going to first build the priority queue, and we can do that in linear time using bottom-up construction method. We have to, every edge comes off the priority queue, so there's E of them, and it takes log E per operation. And then union operations, every vertex is involved in one, and connected operations, every edge is involved in one. So the total time is dominated by the E log E for the priority queue operations. One thing to note is that if the edges come in sorted order for some reason, it's almost linear. The order of growth is E log star V. Actually, we don't have to always sort them. We can, in real life situations, we can stop when we get the V-1 edges in the MST. When we have those V-1 edges, we can stop, and usually that's for practical situations. That's way before we see all the edges in the graph. So that's Kruskals' algorithm for computing the MST.